Hello, welcome back. Today we will talk about arithmetic coding. As we mentioned last time, arithmetic coding is based on SFE code, the Shannon alias code that we discussed last time. And just as in SFE code, every code word can be seen as a segment between the interval 0 and 1. Let me give a quick review. Let's say for a code word 1 1, that will be correspond to an interval from 0.11 to 0.111 dot. This is basically in binaries. So in decimal, it would be like 0.75 to 1. And know that the length of the code word increases as the width of the segment decreases. More precisely, the length of the segment, let me call this wx, is equal to 2 to the minus the length of the code word lx. And remember that, like for the SFE code, basically we partition this interval from 0 to 1 for each of the symbol. Let's say if I have P A is equal to 0.1 and PB equal to 0.3 and PC is equal to 0.6, then basically I will assign the segment, the interval from 0 to 0.1 for A, and then from 0.1 to 0.4 for B, and then from 0.4 to 1 for C. And note that because we have the length of W, length of the segment is equal to 2 to minus Lx, we have the length of the code word is equal to minus log Wx, something like that. And if we assign this length of the segment to be very similar to Px, then we will have the optimum code word length. Remember that if I have Lx is equal to minus log Px, then the expected length will be just equal to the entropy, and that will be the optimum. That is equal to expected minus log Px. So therefore, basically we just want to assign the code word to correspond to a segment that with length very much close to Px. So for the SFE code, we are just going to assign the segment inside the segment for the corresponding symbol. For more detail, you can just go back to watch the previous lecture that we talk about SFE code. But for here, for arithmetic coding, what we are going to do basically just apply SFE code many times. So for SFE code, if I have a symbol B, basically I'll output the code word immediately for the code word B. So we have basically a fixed code word for each of the symbol. So we have CB and CA are basically some fixed predetermined code word. But for arithmetic code, we are going to process many symbols before we are trying to figure out which is the segment. For example, if I have the input of input sequence is something like a short sequence, let's say CBC. So that will be corresponding to, let me draw it longer. Then the first symbol will basically constrain that the code word you have an segment lying between 0.4 and 1, because that's correspond to the first symbol C here. So now I can go down one more step for the second symbol. I think of like, okay, the first symbol will force me to lie inside here. Then I can partition like 0.4 to 1, this interval, further down proportionally to smaller intervals that for A, B, and C for the next code word, for the next input symbol. So therefore, like for input CB, I need to ensure that my code word will have an interval lying between this segment here. And for the first symbol, again, like in this segment, I will further partition this interval into like tiny, it's a little bit hard to draw, A, B, and C here. And so therefore, like, since the input is CBC, I need to ensure that the segment, maybe let me use another color, has to be lying inside here. So I need to basically just find a code word that will have a segment line inside here. So of course, like this can go down. I can have a very long input, and I can just go continuously like partition this interval into very, very tiny interval, and just want to find a segment that is lying inside the interval, and then output the corresponding code word as our encoded code word. Now let's say the input is like a 10,000 B's here. It's basically B, 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 and so on. I have 10,000 of 10. What will be the code word? You can see like the code word will be correspond to an interval with a width basically is 0.3 to the 10,000. So actually you can see the length of the code word will be approximately minus log this, something like that. I don't know exactly the number, but yeah. But you can see like the width of this interval here is really tiny. And how much do we lose in terms of coding performance? You can see that like for SFE code or like for arithmetic coding here, we are kind of losing, depends on like, of course, like how you make your interval to lie inside the required interval. I mean, how do you define the segment of the code word that lie inside the required interval? If you just do it as the SFE code, basically will lose 2 bits out of that. But note that like we are basically coding a block of 100 symbols as one big symbol. Therefore, like the loss in terms of bits would be like 2 over 10,000, and that would be very, very tiny. And of course, like we can, in theory, we can code as long as the source can be. If you have a file is like 1 gigabyte or so on, then loss will be really, really, really tiny and it will be insignificant. And that's why arithmetic coding is so much preferable in practice, because it really can code near the entropy as long as the statistics of the source is given. Another advantage of arithmetic coding is like it can be easily implemented to be adaptive. So for example, if I don't know the probability of A, B, and C at the beginning, maybe I can just uniformly assign that, like A, B, and C is 0.3, 0.3, and 0.3. But as I continue to code the symbol, I can just adjust the width of each of this segment for each of the symbol according to my to the empirical statistic that I obtain from the input source. The only thing I need to make sure is that, like at the decoder, you need to do the same procedure such that everything is synchronized. So therefore, like you can see, like it's very much very easy to do adaptive encoding and decoding. Even though I don't know the statistics of the source right at the beginning, I can compress it rather effectively. Okay, if we go back to this example here, with 10,000 bees trying to be compressed and convert to a code word. Basically, the interval, the segment correspond to this code word will lie inside an interval with a width of an order like 0.3 to the 10,000. It will be like too small even for the precision of the modern computer. So in practice, we cannot really wait until the very end to figure out what is the interval and then compute the code. So in practice, for arithmetic coding, the idea is like we are trying to send out bits whenever wherever we can figure it out, and then I will try to expand the interval. You can think of like we are trying to zoom in. Basically, we have this interval, turns out of the code to be very, very small, and we'll keep zooming into that, so that like we won't have run into like any precision problem. So in practice, the idea is quite simple. So like let's look at an example here. Let's say if we start with the first B here. So remember that we have this is 0.1 and this segment is have width 0.3 and this segment have width 0.6 on length 0.6. For the first B here, what can we tell? We know that the eventual segment of that very long code word had to be lying inside this segment 0.1 and 0.4, and in particular, that segment will be less than 0.5, right? So therefore, I know that the first bit of that code word has to be 0, because if the first bit is 1, that means that the segment has to be lying above 0.5. Therefore, I immediately know that the first bit of that code word eventually has to be 1. And knowing that, what I can do is I can output 1 right away, and at the same time I can expand the interval. You can think of also like I'm zooming in to basically zooming in this part from 0 to 0.5 to 0 to 1. So just basically I'm multiplying the upper bound and the lower bound of the long interval for the moment by 2. So instead I can claim that now my new interval should be lying inside 0.2 and 0.8. Note that when we do this zooming in, we're basically thinking of the code word here for whatever this zooming for the interval that the code word corresponds to the interval at this resolution will be correspond to code word from the second digit and onward. So therefore, like we are not losing anything in the sense, because we already sent out the first bit that we know is 0. And at this stage, when we're trying to figure out like what's the code word for eventually some interval inside here, and represent the code word for this guy here, that code word will be exactly equal to the code word in the remaining second and onward bits there. And we can do the same thing again and again. Of course, if I have the second step, I also have an interval. It's lying between 0 and 0.5. That, let's say, in the next step, let's say I have the first have a B, and second I got an A as an input. If I got an A as an input, I lie inside this 0.2 and 0.8 and 0.1 of that. That is basically 0.26, from 0.2 to 0.26. And again, I know that this is less than 0.5. Therefore, the code word at this resolution, the first bit has to be 0. So I know for this portion here, it has to be start with 0. And again, I can, at the same time, I should expand the interval from 0 to 0.5 to 0 to 1. So therefore, I should have something that I have an interval that is 0.4 to 0.52. And I know that the code word has line within here. At this resolution, I'm basically looking at the code word of this resolution will correspond to the starting, the suffix of the original code word starting from the third bit. So maybe I should use some color. At this resolution, this corresponds to the code word starting from the second bit. And at this resolution, we are looking into code word starting from this bit. And this is the basic idea. So of course, we are only looking at the case when the segment is lying between 0 to 0.5, and in this case, we'll expand the segment from 0 to 0.5 to 0 to 1, and I'll put a bit 0 there. Similarly, if I have a segment that is basically lie above 0.5, let's say I have a segment here that says from 0.7 to 0.8, let's say it's not very much in scale, then I know that the corresponding code word, it has to start with, because the segment has to be, the first bit has to be 1, otherwise the segment cannot be between 0.5 to 1. Therefore, the first bit has to be 1, and then I can basically scale the part from 0.5 to 1 to 0 to 1. So this will give me basically 0.7 minus 0.5 times 2. That's 0.4 to 0.8 minus 0.5 times 2, that's 0.6. Okay, maybe I should put it more like here, 0.4 and 0.6. So, it turns out that the above rules that we just mentioned are not sufficient to avoid the precision problem. For example, if I have A, B, and C have a partition the interval 0 to 1 into something like that, basically, probability of A is 0.1, probability of B is 0.8, probability of C is 0.1, let's say. So if I get many B's, so what's going on is that I'm keep shrinking to the midpoint, so I'm getting smaller and smaller as I receive more and more B. The allowed interval is shrinking smaller and smaller, but still I cannot expand it by the above rule. Because like we'll always have the interval is not lying either like less than 0.5 or bigger than 0.5. Therefore, we don't know what's the first bit, whether it's like should be 0 or like 1. But actually, we can still expand it, even though we don't know whether the segment is going to be less than 0.5, bigger than 0.5. For example, as long as the segment, let's say if I have a segment is like from 0.3 to 0.7, as long as the segment is lying between 0.25 and 0.75, what we can do is that we're just going to still expand it. Basically, we'll expand the interval from 0.25 to 0.75 to 0 to 1. So therefore, the lower bound will be like 0.3 minus 0.25 times 2. That will be like 0.1. And the upper bound will be 0.7 minus 0.25 times 2. That will be 4.9. So what we are going to do is we are still going to expand it as long as the interval is not either bigger than 0.5, less than or lie between 0 to 0.5, or lie between 0.5 to 1. Even when it's lying between 0.25 and 0.75, we will expand it already. But of course, we don't know which bit we should send out. We don't know whether it should be 1 or 0, but it's okay. So it's okay because eventually, let's say if the next step is something like this, let's say in the next step for the next symbol, let's say we have additional constraint that the segment has to be lying inside here. That's less than 0.5 here. So if I go back to the original scale, what I can see is that has to lie inside here, right? So what I know is that it's not just the segment has to lie below 0.5. What I can tell is also it has to lie in the second 0.25 segment, or basically lie in the interval between 0.25 and 0.5. So I know that for any segment lie between 0.25 and 0.5, it will have it basically is correspond to 0.01, right? So therefore, like what I'm saying is that I know that not only I know that the first bit has to be 0, I know that the second bit has to be 1, because it lies between 0.0 to 0.25 to 0.5. For another example, let's say after one expansion, the interval turns out to be bigger than 0.5, like between like 0.5 and 1. Then if we go back to the original interval, original resolution, then basically we know that like the interval has to be lying between like 0.5 and 0.75. So therefore like the first two bits of the code word have to be 10, because it corresponds to a segment 0.10, something like that. So we can see that like I probably need more space here. So if I expand instead of 1 times, let's say if I expand 2 times, let me quickly draw something. Expand 2 times, let's say, first time I have an interval is between 0.25 and 0.75 that I expanded once. Okay, maybe I use this pen to show interval. And then okay, in the next time in this resolution, again, it find an interval, it's between 0.25 and 0.75. Therefore, we expand it again. At this resolution, I have this 2 segment here. I guess I probably should draw a little bit closer on this side. And then let's say at this moment, I find that the interval is lying bigger than 0.5. That's here. So what I can tell is that if I go back to the original resolution, now it's not only it has to be bigger than 0.5 and less than 0.75. If in this resolution I have something like this, I guess, in this resolution I will have something like this, even smaller. So it's not only that this segment will lie between 0.5 and 0.75. It will actually lie between 0.5. Okay, this actually I didn't draw too nicely. Maybe I should draw. Let's say this is the segment. So if this is the segment, this is the segment, and segment for blue is something like here, segment for green is somewhere here. So what we can see is that in this resolution, I will have this green segment, that's the segment that we are interested in, will lie between 0.5 and 0.075. But if we go down to the original resolution, it will be actually lying between 0.5 and 0.625. So therefore, what can we tell is that we can tell not just the first bit and the second bit, now we can tell even the third bit. The first 3 bits of the code word therefore has to be 100. Hopefully, I guess that you already see the pattern. Basically, if we expand the n time in general, what we need to do is just padding n bits that is opposite to the first bit. So for example, if it turns out that we find that the segment is above 0.5, then therefore we should output the bits as 1 and then n zeros. If on the other hand, if we have the segment turns out to be on the other side, then we will need to the output bits will start with a 0 and then n1. And that's basically the whole the entire it concludes the entire arithmetic coding scheme here. They have some more details in terms of implementation. I've included code here, a link of the code. You can go check it out. I guess I will just run through an example quickly. So here is the example. Basically, the input variable can only take 2 values, a and b, and the probability of a is 0.25 and probability of B is 0.75. Therefore, like, we have, something like, A occupy the area from 0.25, from 0 to 0.25, and B occupy the area from the length from the segment from 0.25 to 0.75, to 1. And the input sequence is basically BBA, BBA, BAA here, as shown here. So, now, because the first input symbol is B, we know that, like, the code word should have its segment will lie between that's 0.25 and 1. So then, we cannot do anything yet here. And then let's look at the second input symbol, that's B again. Then we shrink the possible region to about like 0.4 something to 1. And then look at another input symbol A. Then we shrink to this region here. Now this BBA, this region here, is lying between 0.25 and 0.75. Therefore, we can expand it. And again, after expansion, it's still between 0.25 and 0.75. Therefore, we expand it again. So after the expansion, we still cannot output any bit yet. So we look into another input symbol B. And then now after this another input symbol B, we have this region, allow region become this one here. And then we look at another input B. Now the allow region between from here to here, this segment is actually bigger than 0.5. Now we know that the first bit has to be 1 now. And because we have expanded twice without outputting any bits, we need to add 2 zeros afterward. Now we look at another input symbol that's A. Then, therefore we line in the segment is here. And is lying between 0 and 0.5, therefore we can output 0 now. And after outputting the 0, we will at the same time expand it to this segment here. And it's actually, after expanding it, it's lying between 0.25 and 0.75. Therefore, like, we are expanding it again. And afterward, we cannot send out any bits, so we just look at another input symbol, that's B. And then, like, we have this segment become this one. And look, then we read in another input symbol A. Now the segment become this one. Now, this segment is lying between 0 and 0.5, therefore we can expand it. And because previously, actually, we have expanded it once, that's this one here, without outputting any bits. Therefore, we should add a 1 after the 0 here. And then we just keep expand it again because it's from 0.25, 0.05, 0.75. And I get this one here. And then when I have another input symbol A, my new segment become this one is less than 0.5. Therefore, I output a 0. And because I have expanded once without outputting any bits, therefore, like, I should add a 1 afterward, and so on and so forth. That's how we do encoding. Now, let's look at how we decode. It's very much similar to the encoding counterpart. So what we are going to do is that we will first read out some number of bits here, like, or here, actually I'm missing a 1 here. The bits, it basically without 6 bits here. 1, 0, 0, 0, 0, 1. I'm reading this that I know the interval has to be from 0.100001 to 0.10000011, something like that. So it's about here, it's about like 0.5 something to something. So since I know that the interval is here, as you can easily see that the first symbol has to be B, as it lies in the B region here. And then the second symbol also has to be B, because it lies in the B region of, given that the first bit is B, right? If it lies here, that will be the second bit, second symbol will be A. Now, because lie here, therefore the second symbol is B also. Now, because it's lying in the A region of the BB part, like this is the BB segment, so this is the EBA, this is BBB, therefore like it has to be, the first symbol have to be A. Afterwards, like we have this region here, that this red region here, is lying between 0.25 and 0.75. So just as in the encoder, we're going to expand it to 0 to 1, to expand the interval from 0.25 to 0.75 to 0 to 1. So after expansion, we have this interval here, and it's still between 0.25 and 0.75, therefore we expand it again. And after expansion, note that I also width up one more bit. So I just want to make sure the interval have the same position, that the length of this interval does not expand as we expand. So because I width up one, the input bit is 0, I'm at this location here. Actually, if my input bit is 1, that I should have this interval is slightly shift to be somewhere here. Now after another expansion, I should width out another bit 1 here. So now my bits turn out to be somewhere here. No, the interval of the correspond to the code is somewhere here. So line has line in here, and this is basically line in the range of the B part, right? Because given this BBA segment, that's the BBA segment, this is the A part, this is the B part, therefore I should have the output symbol to be B, and then again, like afterward I still have, this one has still B here. Okay, for this segment here, this is the B part and this is the A part is lying on the B part, therefore the next output symbol is still B. And then afterward, this segment is bigger than 0.5, therefore like we should expand it and at the same time it's within another bit. I might get somewhere here, and now it's lying in the A segment here, therefore I'll put an A here, and so on and so forth. So basically that's all I want to talk about for arithmetic coding. And as I mentioned, I have this sample codes that I have put the link of the sample codes on the comment of the video, description of the video, that you can just go look at it if you're interested. And for those who are really interested in arithmetic coding, I also suggest you to read the original paper. Actually, the original paper is very well written, and at the same time, it has the source code written in C, I think, is listed in the paper as well. So, but hopefully this video is helpful for you to understand arithmetic coding. So this basically concludes what I want to talk about for source coding. In the next segment, we'll start talking more about the information measure beyond channel entropy. Basically, we will talk about conditional entropy, mutual information, and so on.